Okay, question 6, the final one. So the calculate the tensile force required to produce a pre-strain rail required by the engineer. Well, it tells us the Young's modulus, it tells us this amount of pre-strain change there, and it says the engineer decides to use this pre-strain of 3 times 10 to the minus 4. So we know that the Young modulus equation, E equals F over A times L over delta L. We can rearrange that to make the force is the Young modulus times the area times delta L over L, which is of course this bit here. And we know that the pre-strain, they told us a value for pre-strain, so the delta L over L, which is the strain they've given us, is this bit here, and that is 3 times 10 to the minus 4. So just plug it in. 2 times 10 to the 11, 7.5 times 10 to the minus 3, 3 times 10 to the minus 4, that's this bit. And it gives us 4.5 times 10 to the 5 newtons. Sorry. I'll be finishing in a minute. Yeah, I'm talking to myself, I'm loving it. Then over here we got, we've lost my train of thought now. Elastic strain energy E equals half force times change of length. We know delta L, of course, is strain times the original length, so we want to know what delta L is. We know that strain is delta L over L, so delta L will be strain times by length, so that's how I've got that in there. So delta L is strain times 45, it told us a 45 minute thing. So it's half times the force times delta L, which is that bit there. That gives us 3 times 10 to the 3 joules. Then finally, we know that the pre-strain, let's get this on the screen, the pre-strain is 3 times 10 to the minus 4, and we know that it changes by 2.5 times 10 to the minus 5 per degree. Yeah, so basically we've got to divide that by the 2.5 times 10 to the minus 5 per degree, and that gives us a value of 12 degrees before there's no strain in it. So 12K is going to be what takes out the pre-strain. We laid it when it was 8 degrees, so it will have 0 strain at a temperature of 20 degrees C. So that's obviously 8 plus 12 is 20. And then it says, why does he not use the highest observed temperature at the location of the railway track? Well, the first point is because it can withstand some compressive stress before it distorts. Yeah. Therefore, we don't by not making it the maximum, then it means we don't have as much force required to lay it. And I suppose the final point would be that it's hardly ever going to be the very highest temperature anyway. So it's probably best to have a bit of strain in it most of the time. All right, that is it. Question 6. You're done.